Welcome to Chapter 4, Global Unicast Addresses, or GUA. These PowerPoints are created by Rick Graziani. This goes along with the book IPv6 Fundamentals, a straightforward approach to understanding IPv6, written by Rick Graziani. He also prepares live lesson fundamental videos for the same material. They go a little bit more in depth than the PowerPoints, but this is a good overview. Again, he wrote the book. He also wrote created the videos. There are the ISBN numbers for both. So let's get right on in. The purpose and format of a GUA. So with an IPv6, we have our unicast, our multicast, and our anycast. Here we're looking at our global unicast addresses, 2000::3. So with that said, let's go and look at the source. IPv6 source is always a unicast address, whether that be a link local or a GUA. IPv6 destinations, unicast, multicast, or anycast, as opposed to IPv6, as opposed to IPv4, which is unicast, multicast, and broadcast. No broadcast in IPv6. So we're looking at a global unicast address. That means the first hextet is going to range between 2000::3 and 3FFF::3. It's a globally unique and routable address. It's similar to a public IPv4 address. 2001 DB8/32, as its reference to the RFC 2839 and RFC 6890, reserves this range for addresses for documentation. These are the addresses I will be referring to the most. So, why 2000 to 3FFF? In a global unicast address, the range will be between 2000/64 through 3FFFFF all the way through 64. That's because they have dictated that the first 3 bits in the 128-bit address will be 001, period. Meaning we have 2 combinations that we can do. We can do any combination between 2 and 3. Why 2 and 3? Because when you break down these numbers into binary, those are our options. The first 3 bits are locked in 001. That's why we can have either 0010 or 0011. Hence the 0 or the 2 or 3. The zeros because we start with 0 and they can range anywhere between 0 and the last number. We're doing hexadecimal, so the last possible number is going to be F, which represents 15. So 1/8 of the IPv6 address space is used. IANA's allocation of IPv6 is again that 1/8. We also have things like our global unicast, our link local, our multicast, our unspecified loopback and embedded, and again, our global unicast. Except under very specific circumstances, all end users will have a global unicast address. The point for IPv6 is to allow for end-to-end communication, end node to end node. Doesn't matter the network, doesn't matter anything. There are enough addresses, so the goal here was end-to-end connectivity. However, there are some networks that use just straight link local addresses, so they do not get a global unicast address. It's important to realize here that a interface can actually have more than one IPv6 address. You can have both a link local and a global address. For example, my link local address is listed. My IPv6 global address is also listed. So I have a 2001 GUA address and an FE80 link local address. Terminology for us to know is prefix and prefix length. Again, the prefix is the equivalent to the network portion for IPv6, and the prefix length is going to be more of the subnet mask portion. And then the interface ID is more the host portion. So here we have a IP version 4 unicast address, 32 bits. We have the network portion and host portion. And the subnet mask would dictate where the host portion may be. And it would move depending on our subnet. With an IPv6 global unicast address, same general concept. We have a prefix. Here we have a subnet ID. So with a 64-bit interface ID, that's 18 quintillion devices. So that's more than we'll probably need. The 16-bit subnet ID initially recommended up to 65,000 subnets. But again, I mean, we're dealing with such large host quantities that our groupings can actually be slightly lower than that. Our global routing prefix subnet, again, will have our general rule, which is a 314 rule. I've heard different information about this. That's where the first 3 hextets is going to be our global routing prefix. We'll have 1 for our subnet, and we'll have 4 for our interface or our host portion. Because again, the first 3 hextets, the 4th hextet, and then the remaining 4 hextets. That gives you plenty of space. But again, we're talking quintillions of addresses. So let's go ahead and let's move on to the subnetting portion of IPv6. That's always a fun topic because subnetting with IPv4 was a pain. With IPv6, it's supposed to be a lot better. Okay, so here we're going to try to do increments of 1. Because if we do a /64, our grouping will be groups of 1. So 0, 1, 2, ... 3, 4, 5, 6, 7, 8, 9, 10, so forth. Because again, if we would do the 3, 1, 4 rule, the first 3 network portions are going to stay the same. It will only be the 4th hextet that will change. Because the first 48 bits, part of the global routing prefix, will stay the same. We're only manipulating the 16-bit fixed subnet ID. That's it. So, valid abbreviations to remove the leading zeros. You can remove all the zeros, so it'll be 0, 1, 2, so forth. It is highly recommended to not subnet into the /64 interface ID portion of the address to configure the subnets. The only exception would be for network infrastructure router-to-router links or router-to-switch links. Networks with an end system attached should be a /64. Essentially, stay out of the interface ID portion. That's what they're getting at. So again, here will be a 314 rule. Is it? No, here we've changed the subnet ID portion to be a 32-bit portion. So here we're going to be looking at the 323 rule. Again, it is highly recommended to not go into the interface ID, the /64 portion, which we're doing here. The only exception again would be router to router, router to switch. Here's the prefix. Here are the interface IDs. But we start ending up with huge amounts of possible networks and huge amounts of, again, possible host IDs. We normally want a subnet on a nibble, which is a 4-bit boundary. Makes it easier to list the subnets. We don't have to, but they're recommending that we do. So we could do like a /68, /72, /76, /80. They want you to stay on an actual whole nibble. You could do 69, but again, then you start getting into really weird things. Here we have the example of 72, which we're going to be able to break into a hextet, and it makes it more complicated. Because again, we have to be able to take the hextet, take the second hexadecimal number, break it into binary, and we're manipulating the number 4th bit, or the which is technically the bit that represents number 4, but we are this row right here. Which is the 4th row, because 1, 2, the row that represents 4. That's why our increment increase has been by 4. The first two leftmost are the subnet bits. The last two on the right are the associated interface ID. This is getting way more complicated than what it needs to be. IPv6 has plenty of addresses, hence the stay on the nibble, range. Again, we could do 79. Using RFC 6164, using 127-bit IP version 6 prefix on inner router links is possible. Built-in limiters with options to tune. There are different ones for iOS, iOS XE, things of that nature. Ping pong attack, neighbor caching intrusion are some of the issues. There are mitigation techniques for both. So if we want to use a /127, reserve a separate /64 for each of the /127s. That's a lot of wasted space. So, this is why we do a /27, 127, sorry, and so forth and so forth. Because that bit will be either a 0 or a 1. So if we do a /64, that locks in the first 4 hextets, and we will then subdivide that into 2 groups with a /27, 0 or 1. This represents all of these addresses, which is a huge waste of additional addresses, but that's what we're going to be doing. All zeros can be confusing, so again, let's go and do the double colon. If we do a 48-bit, we can start manipulating again the remaining bits. So forth and so forth. So we need to be careful which 2 interface addresses we choose. A : 9 and a : A are not on the same 127 subnets, even though 9 and A are right next to one another. Got to be careful with that. Same thing with subnetting with IPv version 4. You have to make sure that your appropriate hosts are on the appropriate networks. Here we have the RFC 1878, the VLSM form. We did this to conserve IP version 4 addresses. Managing a limiting space, we can do that through VLSM. We use /30s for point-to-point links. IP version 6 address conservation, and it doesn't need to be as aggressive as IP version 4, meaning we can get rid of a lot of the /30s, the point-to-points. It's developing an address plan that, first of all, makes sense from the beginning. We're not wasting addresses. It'll be easy to manage. And there are different techniques. So we can do the best current operation practices, BCOP. And here we aim to provide the general IP version 6 subnetting guidelines. Cisco also has the IPv version 6 address guide. And a big part of this is also dealing with the preparing an IP version 6 address plan, or the RIPE plan. There are plenty of implementational guides and plans and organizers to help get IPv6 out there. So let's go ahead and move on to the IP version 6 address allocation phase. Here we have a /23. Obviously, that is not on a nibble, but this is a minimum allocation. This is the RIR number, also known as the Regional Internet Registry numbers. That's why they are the minimum. Moving forward, we have an ISP prefix. We could have a site prefix. We could have a home prefix, or maybe a state prefix, or a county prefix. We could also have a subnet prefix. Am I getting a /64 address at home? Some people really are. Not everyone, but some. When we look at the prefix, we can determine how many subnets we're going to get. For example, if we do a /60, we're going to end up with 16 64-bit interface IDs or subnets. If we do a /56, we're going to end up with 256 64-bit interface IDs. If we do 52, we're going to end up with 4,000, so forth and so forth. Many sites are getting the /48. That is 65,536 possible networks of 64-bit interface IDs, which again are quintillions of addresses. The provider independence, the PI address space. We have our regional internet registry, which is a /32. The remaining addresses to the customer regardless of the provider. No prefix renumbering needed if you change providers. That's been a huge plus. We have a provider aggregate table address space, which is a PA. The address space that is typically assigned by the ISP to its customer. If we change our providers, we will get new address spaces for that portion. Customers do prefix renumbering. So let's go ahead and get on to our GUA Static Configuration. Again, the GUA is a global unicast address. We're going to talk about link local addresses in lesson 5 and multicast in lesson 6. So in global unicast address, we have two major types, manual or static versus dynamic. Under manual, we have static plus EY64. We have the unnumbered IPv version 6. Under dynamic, we have Slack and DHCP version 6. Slack is stateless and DHCP is stateful. We're going to get into that. With Slack, you do have a Slack plus DHCP. And with DHCP version 6, you have a DHCP version 6 PD. Details including Slack, which is again the stateful addressing auto configure. We're talking in lesson 7, and DHCP has its own chapter, so this is only for an overview. So, how do we configure static GUA? You get on an interface. It's exactly the same as an IPv4 address, only slightly different. First of all, instead of typing an IP address, you type IPv6 address. Type in the appropriate address. Here, instead of a subnet mask, we're doing the CIDR notation. We're going to do the slash notation. So, /64 without spacing. We turn it on, and you should be good to go. iOS commands are very similar. All zeros and ones are valid hosts in the IPv6 address. So we got to be careful with that. So how do we configure again? We could start manipulating again, because if we're following the appropriate 314 rule, we're going to end up with two networks, two different IPs. In the fourth hextet, we're manipulating them by 1. That's what's separating the networks. IPv6 unicast routing. This command is a global configuration command is required to forward IPv6 packets. It is not required to configure the IPv6 address. Meaning, if we want to run IPv6 on our router, we need to, in the global configuration, type IPv6 unicast-routing. So let's talk about verifying the addresses. You can do a show run, and you want to go to the interface, and you're going to be looking at the appropriate configuration for that interface. You'll notice it'll say no IP address. That's because the IP command is by default IP version 4. That's why we need to type IP version 6 or v6. That will denote our IP version 6 address. We may have two interfaces. So we may have a single interface with two addresses. Our interface could have a link local and a global unicast. The link local addresses are automatically created, and that will happen before the global unicast addresses. The link local addresses are used for communicating with other devices on the same link. It's like a private network, non-routable. Link locals do play an important role in IPv6 networking, so we have to make sure we have a good understanding of what link local addresses are and how they function. We will discuss more in detail in lesson 5. Here we can assign a IPv6 address to a Windows machine using both the address, the prefix, and the gateway addresses. So one issue to mention here is that even if a static address is configured on the host, it's still possible to pick up a Slack address. In other words, configuring a static address does not mean that it will be the only global address on the end user's system. If the router is sending RA, the hosts could get both a static and a Slack address. That's where we can have multiple addresses for one device. It can also be a link local unicast address of the router. We can always verify addresses on a PC by typing ipconfig or ipconfig/all. we will get the appropriate IP version 6 addressing information, both the IP version 6 and a link local address. And by default, Microsoft does use a random 64-bit interface ID for the link local addresses. More details coming soon about that. And again, the default gateway. We can verify it by pinging them, just like you would do any end-to-end connectivity, whether IP version 4 or IP version 6. Could we do a IP version 6 general prefix? The general prefix option can be used as a shortcut or alias for just about any command requiring IP version 6. We can actually set a general prefix with a name, the network nodes, and the appropriate prefix. This will allow you to do a general prefix. That way, instead of having to type in the networking portion, the actual network prefix, you can just type in the name of the prefix. And that way it automatically knows the first 48 bits is part of the prefix. That way it kind of speeds it up. You can also do a show IP version 6 internet brief. Again, instead of an IP interface brief, this will show the appropriate IP version 6 commands. Here, the my GUA, it will actually take the first three zeros. These are really the code for these. That's what the arrows are meaning. That means the 88 and the 99 are that fourth hextet. Moving on, the general prefix renumbering. Again, we can have this as the general prefix. We can turn it off and then turn it back on so that we can again update them. Again, it will be the renumbering. So let's go ahead and look at the configuring a static GUA. Because again, under our global unicast addresses, we have manual and dynamic. So let's go and look at the manual, specifically the static plus EUI64. So we can configure the static GUA plus EUI64 by, again, doing a question mark at the end, and that should give us the EUI64 interface identifier. The criteria, all zeros, is okay. So we can end it with an EUI64 that will use the appropriate 64-bit interface ID, which is created with the EUI64 using the interface. And we're going to be using the 48-bit MAC address, and we're going to be inserting a 16-bit FFFE in the dead center. We're also going to be flipping the universal local bits. So let's talk about that. Here we have there it is. We have 1, 2, 3, 4, 5, 6 pairs of numbers. First 24 bits, the OUI. The last 24 bits is the device identifier. We separate them in half. We insert the FFFE. We then actually manipulate the 7th bit, the UL bit flip. So if it was originally a 0, we flip it to 1. And that is our extended unique identifier, that our EUI 64-bit identifier. So let's look at configuring a static GUA with an EUI64. Again, we just put it at the end, and it will take the MAC address. It will, again, separate it, put FF, FE in the middle, and then flip the 7th bit. The prefix will come down, and we're only doing the EUI64 is going to be the interface portion. Again, it's going to use the 48-bit MAC address. So let's go ahead and do an overview of dynamic IP version 6 addressing. Again, this is just an overview. So we can do the dynamic addressing. With DHCP clients, we would do a DHCP request and acknowledgement. It would go back and forth until we were assigned an appropriate IP version 6, an IP version 4 address. With IPv6, we can do the same thing. We have an ICMP version 6 protocol, similar to ICMP for regular ping, but here we have an ICMP version 6. ICMP stands for Internet Control Message Protocol. With ICMP version 6, it's more than just a message, but more of a how IPv6 conducts the business. There's the appropriate RFC 4861, and that's used in the dynamic address allocation. Again, this is just an overview. We're not discussing it in depth. ICMP information message is used by neighbor discovery. We have an RS and RA message, router solicitation, router advertisement message, and that's used for dynamic address allocation. Router device messaging, neighbor solicitation, and neighbor advertisements. This was used with IP version 4 ARP, and that was used with DAD. Device-to-device messaging. We also have a redirect message, which is similar to the ICMP version 4. So let's go and look at the ICMP router advertisement, or RA. From the router, the router advertisement will suggest to all IP version 6 devices on the link how it will receive IP version 6 address information, and this will be sent periodically by the IP version 6 router, or when the router receives a router solicitation message from a host. Maybe a multicast. To all IP version 6 routers, I need IPv6 address information. That will be a router solicitation, which is different from a router advertisement. Multicast to all IPv6 devices, and then it will return with a router advertisement. So you need to understand what the router solicitation and router advertisements are, and what causes or what generates a router advertisement. With a DHCP version 6 server, you may not even need it anymore. Router advertisement messages, part of the ICMP version 6 protocol. Again, we enable it by IP version 6 unicast routing. We will send a router advertisement message or sent by an IPv6 router. That only happens when you run the IP version 6 unicast routing command. It allows for forwarding of the IP version 6 packets. It enables IP version 6 dynamic routing. It enables sending of the ICMP version 6 router advertisements. Routers can be configured with IP version 6 addresses without the router being an IP version 6 router. You have to type IP version 6 unicast routing. Sorry, I had to repeat that several times because it's a common mistake. I enable IP version 6 addressing, but it's not working. You have to make sure globally to enter IP version 6 unicast routing. That turns on the IPv6 routing capability. IPv6 static routes can be configured, but the router will only forward locally generated packets. So let's go ahead and go through this again. Option 1, we could do Slack no DHCP. That's the default on a Cisco router. I have everything that you need, the prefix link, and the default gateway. Option 2, Slack with stateless DHCP. And the DHCP is going to be mainly for DNS. Here's my information, but you need to get other information such as DNS address from the DHCP server. Option 3, all address except the default gateway will come from the DHCP version 6. I can't help you, you got to talk to the DHCP server. So there are 3 different ways to do the router advertisements. Most common, again, will be Slack no DHCP. Again, that's the default for Cisco routers. You can send the DNS server information in a router advertisement now. Options 1 and 2, DHCP servers do not maintain state of addresses. Option 3, it's stateful, so it does receive and track address information. So again, under dynamic, we've talked about Slack, we talked about DHCP, but for more in-depth information, we're going to cover that in Lesson 7. For DHCP, Slack and DHCP PD, that's all Lesson 8. Lesson 9 and Lesson 10 will cover ICMP and ICMP neighbor discovery. That was it for the end for this chapter. Again, this was chapter 4 in the IPv6 fundamentals, a straightforward approach to understanding IPv6, written by Rick Graziani. Again, Rick Graziani owns all rights to these PowerPoints. This is the appropriate ISBN number for both his book and the fundamentals videos. Here's his contact information. This was Chapter 4, Global Unicast Addressing. Again, thank you.